Let's go ahead and get started today. Today's just going to be a review, so I'm going to do a couple that I know you guys are going to want to know, and then if there's time, I'll start asking around for those types of questions, right? So I did a fair amount of review last time. Something that is really funny that I didn't notice until yesterday, nobody told me that the videos on this are mirrored. So I don't know, people watch them, but nobody told me. So they're the wrong direction. So I'm going to try and get those fixed before the weekend on like Friday or something, but YouTube doesn't have an easy option to just flip them the right way. Because I know people like to go back and watch for review purposes, and I imagine it's very difficult when the letters are wrong. So I'll try and fix that. Anyway, so last time, right, we covered a fair amount. So now I'm just going to go through homework questions, because most of your questions on the exam are going to come from the homework. Well, all of your questions are going to be homework related questions, lab related questions, or lecture related questions, right? I try and make sure that you have some homework or lab of every type of question, so that it's not just material in the lecture. I can't promise that there won't be something that's from like the book content, but you guys have open notes, open book for the exam. The exam will be on Tuesday. If you fall ill, contact me before the exam and let me know, because I don't want you here if you're going to get everybody else sick. I don't want you failing because you take an exam unwell. Try and make it on time. It's easier for you and everyone. Don't try and just extend time, and that statistically actually doesn't do anything for your grade. So don't think you're clever by pretending to be sick, because it actually doesn't help. So open notes, open book. I really don't care about digital notes. You're totally fine to use computers. Be aware if you think you're clever and you're going to go connect up to some internet chat line and try and help. I have scripts that monitor for that. They're just going to watch for homework questions for my exams. And I also like to post fake answers. I have a lot of fake answers that are out there for my exams. Yeah. Yes, I put in the wrong answers out there on purpose, so if someone goes and tries to use the internet to cheat, they use my answer and they get a 0 on the exam and they fail the class. Yes. Oh. Yes, I had 2 last year that failed the class because they thought they were clever. I think it just almost feel like it's equal at the same time. All I have to do is not do that. So I think one of the hardest questions from homework 2, which is really not that hard, hopefully at this point, right? Homework 2 is probably kind of confusing when you got there. I've already posted the answers to homework 1, and I will try and post all the answers to. My goal is Friday for all of the other homeworks. That means, much like you guys, I put off my homework till the very last day and I have to do it all at once. But this one, right, this might be confusing, and there's kind of 2 ways to do it. The obvious way is to ignore the output bubble for the moment and realize that there's 2 input bubbles. That makes this what kind of gate without the output bubble? What kind of gate is that? NOR. So that means I can redraw this as a NOR with the output bubble, which is an OR gate, right? So that gate is just a weird way of drawing an OR gate. If you're not as adept, if you're not as comfortable just looking at things and seeing those kinds of patterns, the kind of brute force way of handling this is break it out into all its separate components. Right? And then you can go through the analysis of this, which is to say, if this is A, this is B, this is not A, this is not B. That makes this not A and not B. That makes this not that. Right? How do I solve this kind of problem? Morgan's theorem, which is to say that I invert each of the variables and I invert the gate. So right, it's not A or not B, which is the same as A or B. 2 different ways that work very well to analyze that kind of question. We of course have more sophisticated, difficult analysis type questions that we can do. Y, Z, X comes down here, Z comes there. There we go. Right, good question for this type of circuit is, of course, analyze the circuit, which is another way of basically saying find you have X, Y, Z. I think F should be sufficient. Find F. Right, what is F? What does the circuit do? Is all analysis is saying. This one is always just be careful, keep it nice and orderly. The cleanest way, the most organized way is to give it intermittent variable name, the intermediate node variable names. And since we're here, X, Y, Z, I can just start at A and just say A is X or Y. Then I come down here, this node doesn't really need a new variable name, right? Because it's just an inversion. So this is simply just not X. I could give it a variable name if I wanted to, but it's just as easy to say it's not X. Up here, this guy, right, we're looking at Y, X, or Z. That is drawn as so. Right, remembering the XOR is just saying if one or the other is true, but not both. So there's another way that we could write XOR, right? We could just use the min terms on this one. And then you have another way of writing XOR, or you can write it that way. Either one is correct. I'm not going to be that picky on you. Just as long as you understand, right, the relationship between the gate and the truth table, you'll be good to go on these ones. There's a fair chance you'll see an XOR on the exam. Then this OR gate, we just push through and see what is this. So this, I'll make that B. This then is C is equal to B or not X. And then F is simply equal to A XOR C. Makes sense? Then I went on. How many of you actually started homework 6, the last one that's all timing and everything? I'm very proud of all of you. All 3 of you. You outperformed the night class once again. Only 2 of them had started.
We're beaten by 1.
Yeah. So anyways, this is A XOR C, and then we can just substitute the X or Y. XOR C, which is B or not X. My substitution isn't done yet, right? Because I still have a value for B. So now I have X or Y. X or B is Y or Z. Y X or Z rather. I don't ask to simplify, you're done. In general, I'm not going to ask you guys to simplify XOR circuits. If I do, I will try and put a reminder that it's easier to simplify if you write the min-term version of this rather than the XOR, because we don't really have any rules or theorems that I've taught you that uses XOR, right? So it's easier to write it as that's XOR, right? This is saying if B is true and A is not, or A is true and B is not, then it's true. Okay, anyways, on exam or homework 6, not the exam 6, homework 6, I actually give you the same circuit again. This exact same circuit. The question is different this time. The question is identify the static hazard. Now in homework 6, I don't tell you whether it's static 0 or static 1, right? And you can't necessarily immediately tell, because we know that if I have sum of products, I get a static 1 of hazard if I'm going to have one. And if I get a product of sum, I'm going to get a static 0 hazard. Static 1 meaning it's supposed to stay at 1 and it dips to 0 when there's a transition. And static 0 meaning it's supposed to stay 0, but it bumps up to 1 when it shouldn't change. So our steps in order to identify, is there a static hazard, right? That's the first thing, is you could be given a circuit and I might have it say something like, identify if there is a static hazard. If there is, identify it through the use of a timing diagram, right? So for this one, is there a signal that has a potential to be a static hazard? Yes, X and Y. Why are they potential for static hazards?
They have a different number of gates between them and the end.
Yes, they have delay paths of different lengths. They have more than one path, and those paths differ in length. So what that's saying is that X goes through 1, 2 gates to F, and it goes through 1, 2, 3 gates to F. So the first thing that we need to do is just ask the question, is there a signal? I'm just going to use S for signal. Is there a signal with greater than 1 path, right? Then 2, do those paths differ in number of gates, right? Because if they're the same delay gates, then you guys get to leverage the fact that I've been nice and that we've assumed that all gates in this class have the same delay. Again, bad approximation, but it's a useful learning tool so that we don't have to overcomplicate our lives, okay? So if there is one with a path, X and Y, do those paths differ in number of gates? Yes. Once I've done that, now I need to start identifying, does it have a static hazard? Is there a possible situation that I have a static hazard? So 3, you have to select one of the potential signals. And then prime the gates. Once we're here, right, we could just kind of start guessing and just start with the prime the gates, but this is kind of a formal description of how do we determine if it's even worth drawing the timing diagram? Because it might not be. We might find something like, well, X has more than one path, but it has the same number of gates. So because we have the simplification, I'm not going to worry about it. So what we're going to do then is we're going to go look and say, well, how do we prime the gates? And we have to choose X or Y. Let's just choose X for now. Let's do one at a time. And so then we get to ask the question, how do I prime these gates? So OR gate, I'm looking for X to be able to make the OR gate respond, right? That's what the OR gate is. We want it to function so that if X changes, then the output of that gate changes, both of its gates. So the OR gate, what does that make Y have to be? 0. So we know that Y has to be, I'm going to put it over here, 0. Z. Now, Y, Z are both going into this XOR gate, but neither one of those are signals that matter, right? That's not what I'm testing. They're going to be static. So what really matters is I need X to be able to change this OR gate. So what value do I need the output of the XOR gate to be? 0. So then if I go look at the XOR gate that I erased, I have 0, 1, 1, 0. And that's basically saying that I get a 0 in case of 0, 0 or 1, 1. But Y has to be 0. So what makes Z have to be 0? So that's nice. That's not going to change ever. And now C is going to just follow the inversion of X. A is going to follow X directly. C has 2 gates, X has 1 gate. Now we have to determine, well, is it static 1 or static 0 basically? And the way we would find out, right, is we would just say, well, is X is 1. And if X is 1, A is 1, and we get a 1 at the output. 1, 0, puts a 0 here, makes C 0. Now I have a 1 and a 0 here. So this is assuming that X is 1. I got 1, 0, F is true, right? Because it's just another XOR gate. Okay, now I want to make a transition to 0. And I need to come down here and say 5 and just check if the output is the same for S equals 0 and S equals 1, where S is the signal of interest that we've identified, in this case X, right? So S is kind of my abstracted version. So we need to know, is the output the same, either 0 or 1, as X changes? Because if the output changes, it's not a static hazard because it's supposed to change. It might change at a weird time, but it's not a static hazard. So here, now I check the 0 condition. Everything else stays the same. We're only changing that one signal. I will never ask you to do anything more complicated on the exam. So the 0, that makes this a 0. So this kind of dash notation, I'm saying it starts at 1 / it goes to 0. This one comes down here. 0 becomes a 1. 1 passes through, 0, 1. They're now different, but the output stays 1. Because it doesn't matter if I have 0, 1 or 1, 0 in my inputs for an XOR gate. Either case is true. So now we can say with confidence, because it's supposed to stay 1 at the output, and there's 2 different delay paths, then I'm going to have a static hazard. We can say that with confidence, because if this is driving the 1 and it drops to 0, this node, this wire, will drop to 0 before the delay passes through and raises this to 1. So we're going to get some small window where this is 0 and this is 0, which makes it 0. That's why the static hazard happens, right? These 2 different paths, one of them is just longer. And by doing that kind of quick analysis, I can realize really quickly that it is going to, in fact, be my 1 to 0 transition that's most likely to cause my problem. So let's test the 1, 0 situation. Okay, and I'm just going to say this is X. I'm not going to write the ones that I'm not changing. I'm not going to bother with Y or Z. I'm not going to bother with not X. If you feel the need to, don't be embarrassed, right? It's better to keep track of everything than it is to skip steps and make mistakes. But I think we're okay if I just skip over this and keep in mind that not X goes here and there's an extra gate delay. That's your biggest risk, is losing track of this extra gate delay in the timing diagram if you don't explicitly write not X. And in fact, now as I explain it, maybe it's better that I show Y. I just don't like drawing all these rows, right? So if X does this, let's give it some vertical lines. As just a quick reminder, right, the reason I put these vertical lines is I'm saying that each one of these lines is equivalent to 1 gate delay. And that gate delay can be whatever it is, right? They could be really large, slow gates, and maybe this is a microsecond, or they could be small, fast gates, and it's a nanosecond. Whatever it happens to be, it's just 1 gate delay. Again, oversimplification. So what happens is I'm saying I assume that X is going to drop here. and continue on that, at least for a while, right? I'll have to do the other transition. If it turns out the 1 to 0 transition doesn't work, then I can just do the 0 to 1 transition, because it's going to be one or the other where the static hazard appears. It has to be a change. So X naught will change. I'll do this in black, actually, so it stands out a little bit. X naught will change in response to X changing, but there's that one gate delay that prevents it from changing immediately, right? The gates are not instant. Nothing in the real world is instant. So it takes some amount of time. And these timing diagrams, I will warn you now, are going to become more difficult as we go along. But now we can go look at A. A is probably a good one, right? This is the other benefit of assigning these variables, is how I can say A. And we know that A is X or Y. Well, Y is always 0. So the fact that Y is always 0, it's 0 unless X is 1, right? Because X or 0 is just X. Again, with one gate delay. So
wouldn't your not X be opposite of this?
Oh my goodness, yes.
Well, still, yeah.
Okay, there we go.
Yeah, that would have been very confusing at the end when I didn't have a static hazard or something. A, X or Y just follows X, one gate delay. X is 1 to 0. And so on. We have not X. Don't need to worry about B really, because the output we've already designed B to be 0. We've intentionally made it 0, so we can just remember that B or not X then just follows not X with one gate delay. So not X, but it changes here, one gate delay. That was C. Okay, well now I just look at B or not X goes into, that's C. A is here. Now I'm just doing the operation of A, X, or C. I no longer have to worry about any of these other signals. I'm just looking at A, X, or C, the exclusive OR of these. Well, in the beginning, I have 1, 0, 1, 0, both of that's true. So we're true, true. But here, it drops to 0 while this is still 0. So 0, 0 is not true. So it's going to drop to 0. But because it has to travel through the XOR gate, this transition gets delayed one gate. Drops to 0, continues on. And then here, when it rises back up, that's going to make it true. But one gate delay later, because it have to go through that last XOR gate.
So is that the hazard right there?
That's the hazard. Because in both cases of X is 0 or X is 1, the output should be 1. But it's not. Only if I make that transition, when I change. The static 1 hazard, which is what this is, happens because the different gate delay paths. That's most of the rest of homework 6. Homework 6 is actually excellent for preparing for the exam, by the way.
So that's a static 1 hazard.
Yeah, because it's supposed to stay 1.
So static 0 is it's supposed to stay 0 and go
Yeah.
to 1.
So you're giving us homework to not just make us do extra work.
Yeah, right?
No way.
Okay, let's do a couple K-maps. Especially I want to do at least one of the product of sums K-maps, right? Because we do less of those overall. And I'm probably going to put one. Does anyone need any more time with this? Okay. Right, and I'm not going to be able to review everything today, but between last time and today, we should get most of the most difficult stuff. Once I get the solutions posted, those will help. I will try. I do have some concern. Actually, I'm going to jump to that if I can find homework 3. Where I've actually had a few students that don't yet understand the timing diagrams just fundamentally. And if you don't, really try and reach out to me. Unfortunately, I'm not going to be able to be in my office hours today because I have a curriculum meeting thing that I have to do because we have a new degree coming in our department. But if you don't understand this, try and reach out on like Friday. I'm going to be here all day Friday. And I can meet over Zoom, but if you don't understand these timing diagrams, these are really important and they are not going away ever. Basically, if you go on and be a digital designer, you're going to be staring at these a whole bunch. They're an incredibly useful tool that you will use all through this semester. You'll use all through 3610. And if you take any more advanced kind of digital design courses, they're going to stick. So this is one of the most important kind of things to understand, that when I say A, right, because F is probably an easier answer, which is A, X, or C, right? That's the equation. I'm just looking one at a time, where this is 0, or sorry, A, this is 1, this is 0. Now I have 1, X, or 0, which is true at this moment in time, right? That's what all these timing diagrams are saying. If that doesn't quite make sense to you, we need to talk on Friday or over Zoom. Monday probably would really work as well. Okay.
I'm curious what the new degree is.
Biomedical engineering.
Okay.
Well, so, is it cool? Sorry.
Oh, sorry. It's really a biomedical devices engineering degree. It's very closely related to electrical engineering, but with a little bit.
So are they going to be taking a lot of these classes too?
There'll be a lot of overlap between the two. By design, it should end up being a really cool degree that will get a lot of students what they want. So if I'm just kind of making up a K-map, right, it doesn't really matter the order of my variables, but I do need to specify something like A, B, C, D, knowing then that this column corresponds to A, this column corresponds to B. I think I mentioned last time, and as we're saying again, even though it's open note, open book, I still strongly recommend making a one-sheet summary of things that you believe to be most important. One of those, just put down a K-map, fill in from one of your homeworks, put out the equation, probably one product of sum, one sum of product, just to make sure you don't do things like forget to swap these two columns, right? And just give yourself a nice example. It's always really good. We could go the other direction. I think it's worth doing that now. It'll take more time. So, right, we could go. There we go. Okay, so this is kind of an evil K-map, to be perfectly honest, for the question involved. So there's a couple ways that I can end up asking these types of questions, right? Which is the first thing you need to do is read the question and determine, am I asking for sum of product? Am I asking for product of sum? Or did I not specify? Because it's entirely possible that I could just ask, design the minimum expression for this circuit using the K-map. Right? In which case, maybe the zeros or the ones is a better choice because one of them might be easier to do. In this one, I'm not sure that there's an obvious, easy answer. But I want to point out one thing, that is this table is 0, 0, 0, 0, right? That makes, and it doesn't really matter the order that I write A, B, C, D here, as long as I'm very careful. So what do I mean by that? So my A is here. So the zeros are always the same, and there is a 0 here. Right? I can go the other direction from K-map to truth table just as easily as truth table to K-map, as long as I'm very careful. Because now, if I count up to 0, 0, 0, 1, I need to go find the spot where D is 1 and nothing else is. So that means this first row, and D is 0, C is 1, so that makes this that 1. What? Oh, why do I have another 0 here? There we go. Right, D 0. Oh, I see why I'm backwards. Oh. D, I want 1. There. Ah. Sorry, I didn't get enough sleep this week.
You should go some of your sleep.
So now this is the only C is 0,
It was a lot.
which is the one that I was doing, right? So now we're 0, 0, stay the same row. We just did this one, and now we're looking for C is 1, D is 0. That's that one. Then the next one where we have the 1, 1 is this one. And so on. We can build out this truth table as long as we're careful, right? And if I change around the orders DCBA, I'll build a different truth table, but it'll be the same functional circuit. Now, if I want the product of sums, there's 2 ways that I can end up asking this question. I could say, design me the minimum product of sum expression, or I could say something like, design me the minimum hazard-free product of sum expression. And those are different, right? So the minimum expression just says complete coverage with as few and as large implicants as you can. Well, here our largest implicants are never more than 2. I don't have any more than that. And it's just, it's possible that we're going to end up with like a redundant one, but this is kind of an easier one because we're going to have those zeros, those zeros, those zeros, and then wrap around. There's my product of sum expression. It turns out that the vertical would probably work just as well because I'd have this pair, that pair, that pair, that pair. So you have 2 very different answers that are equally minimized. So there are more than one answer. Okay, so then we need to write this expression, which we go and ask what doesn't change, right? Which is just another way of evaluating which ones are logically adjacent. Well, here I'm going to have some function f is equal to, if I take my first row min term, then I'm going to have a, b, and what doesn't change, c. And what this is interested in, right, d change, basically is what that's saying, is the product of sums cares about where are the zeros. So if I have these zeros, then I have a is 0, b is 0, c is 0. None of them get the bar because we get a bar over the ones in the product of sums. Now we know that all 3 are going to have, all of my terms in this are going to have 3 variables, right? Because they're all circles of 2. And so now I have a, b, and every single one of them actually is going to have a, b in it because they're all horizontal. So in every case, a, b is what's going to not change. So everyone is going to have a or b. In this case, it's not b or d, which is also 1, so not. And then we have the and then we go on here. Now it's a or b, both of them with bars because we're in the 1, 1. Then we identify that c doesn't change and it's a 1. Then we come down here, say this is AB, where A is the 1 now, so not A. And we're wrapping around with B not changing, and it's a 0. There we go. That is the minimum, or a minimum product of sum expressions, right? It's not the only one, but it is a valid answer. However, if it were the more complicated question, I should say, okay, now make this a static free. What do I do? Hazard free. How do I know a hazard exists?
I mean, you can see that they overlap, right? So like you can draw vertical.
Yeah, so I have adjacent zeros that don't share an implicant, which means that there's going to be a static hazard. Specifically, it's going to be a static 0 hazard. And more problematic, there's actually 1, 2, 3 of them, 4 of them. So in order to complete the static free one, I'm going to use black for these. I need to add in 4 more implicants. Now, you can rest easy. I'm not going to have an expression that has 8 terms in it. That's just unnecessary. But right, this was a good example of kind of the worst case scenario of any K-map. If you wanted the most sophisticated, difficult to do. Now I just add a bunch of and terms, and there we go. There's the answer.
Oh, I saw in the homework, I should have asked it, well, done homework earlier and asked it earlier, but when you have a bar over like the whole set of products,
So like
How-
that,
yeah, how would you write that on the K-Mac?
you would have you wouldn't have that term coming out of a K-map.
Okay.
That's not
Not
something that
coming
you do.
out of, but I'm
Yeah.
curious how you write it.
Oh.
into the K-Mac.
Yeah, so if you had like, if you were given an expression, actually, let's see if I can find one, because this is the next thing that I'm gonna end up doing anyways. You don't remember what homework that was?
That was homework 5 on campus. 5 on campus. So it said homework 4 on the sheet.
On the sheet.
Yes.
Yeah.
For recording.
One of the 2 homework 4s.
So bad. So this one.
Was it this guy?
Yes.
Great. So the question is F equals. So it asks you to not simplify. And there's a couple of different ways that you can handle this. One of them is you could, so this is 4 variables, which makes it a 16 variable K-map. And so you could draw out a truth table and then say, well, I have A, B, C, D. And now I want to investigate where is not. Well, let's start without the not. I think it's a little bit easier. Where is AC or AB with the appropriate knots? This is only half the K-map, right? There's 16 columns, but I'm going to see if we can't just do this roughly. So if I have A, not A, and C, so meaning C is 0, I'm going to really need to keep going, unfortunately, because I'm going to need this A condition, just at least a couple of them. A is, there we go. So this column is going to be true if this is true, right? So not AC. So A is 0 is the first 8. C is 1 is here, 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 and here. Then the A is 1 is down here, and not B, which is this one. So that's all 4 of those because B is 0. And then it won't be any of the rest of them because B will go back to 1. Everyone see that? So now what I can do is extend the column and just say not. And if I call this Y is good, or yeah, X is good. Start with X. Call this X. So let's call this row not X. Well, if this is X, then not X is simply 1, 1, 0, 0, 1, 1, 0, 0, 0, 0, 0, 0. Right? So now there's that term. That's taken care of. This is now what I'm calling not X. Or B and not D. Add a column, I go find B, which is this section, and not D. So I get a 1 there, B and not D, and B and not D. There's going to be 2 more down in the remaining 4 rows that I haven't drawn. But this is that. And now these overlap. That doesn't add a 1, but this adds a 1. And now I can say F is equal to the OR operation of not X or B and not D. So anywhere there's a 1, and I now can say 1, 1, 0, 0, 1, 1, 1, 0, 0, 1, 1, 0, 1, and so on. Now we can turn that into a K-map quite easily, right? So there's another operation that you could do that would be just as fine, because it turns out De Morgan's isn't simplifying. De Morgan's is just transforming. De Morgan's is something you have to do in order to prepare for simplification, because we can't simplify something under the bar. So we could say, well, if I call this Y and this Z, then F is also equal through De Morgan's that, which is then equal to not Y, not Z with the ands. And then I can substitute back in to get A bar C knotted and A B bar knotted. And now I can do De Morgan's again, which gives me A C bar or, oops, A or C bar, right? Got to flip the gate. A or B, A bar or B. And then the final expression, I just bring this down, or B, B bar. And now that one's actually much easier, just to write the K-map directly, because I have just 3 OR situations. Yeah, I mean, ends up being a really kind of interesting K-map. And you can always compare it to that one to make sure I didn't do my algebra wrong, right? The truth tables make this really easy to check, because this is kind of, you could do that in one step as well, right? We didn't have to do this intermediate one. I could have flipped these gates and terms and ended up with the same result. And then this is just saying, more or less anywhere I have A, I'm going to have a 1, which we can see is already happening. Anywhere I have a not C, I should have a 1. That appears to be true in our current K-map. And then this is not A, right? So it turns out in this K-map, A is kind of a trivial variable. Yeah, because now you can go and simplify, right? And so I'm not going to stop you on the exam from using other tools to check. So if I ask you to solve something like this through Boolean algebra, minimize this. If you use a K-map to check, I'm fine. It's okay, right? So maybe we'll finish this one off, since I know a lot of people are nervous about Boolean algebra. I just copied down what we already had. Do those parentheses matter?
Yes.
Another way of asking that, is there any difference between this and that. There's no difference. So those parentheses, I like to put them in because they help me keep organized in case it does matter, right? If I ended up back to ands or something, an and operator. But as it is, this is just addition, so those can all fall away, which is to say these fall away. And now I can ask, does the last term B and not D do anything? Another way of asking that, how do I simplify that B and not D term?
It doesn't matter because if B is true, then
Yes,
it's always going to be true.
exactly. If B is true, rather more specifically, if B and not D is true, this will already be true. Another way of writing that is through algebra, which is if I factor out the B, one or not D. What is one or something? It's just one, right? So then that term falls away and I get B. Now I have A or not C or not A or B. Well, what is A or not A? One. So that's one. Or this whole thing becomes trivial. Trivial circuit. Yeah.
On the original.
I probably screwed something up.
Yep. Yeah, you did.
Sorry. And A or not C. Yep.
Okay, there we go. I was actually kind of wondering about that. I'm like, did I do something wrong?
Which is okay, right? Because we can go down and we can see that it's not trivial. And then it became trivial. Good check. But good catch. This one, if we wanted to, there's two ways we could deal with that one for simplification, right? We have a bunch of rules that say things, or you can just FOIL. I really like to FOIL because it makes it really easy. So foiling that one. If you don't know, I assume they still teach FOIL in like high school algebra.
Well, I've been in high school for 5 years, so I guess I can't explain.
Right, it just means first, outside, inside, lasts. It's just saying multiply all the possible combinations. So A and not A, B, C bar A, which I'm going to flip A bar C bar, C bar B. And then we bring over our other term, which is B bar. Now I have essentially 1 or 0 or 0 or 1. This and can never be true. 0. And then we can go through and start trying to factor things or use other identities. But here, if I factor out a B, I just get C or D bar. Here, I can't factor anything out. If I wanted to find out for sure if I'm simplified there at this point, right, I could draw a K-map of this and figure out if there's any more simplification I could do. Because this is the point where in order to simplify further, I would need to, if it's possible, I would need to add another term, right? Sometimes basically the A or A kind of situations. Sometimes that becomes what's necessary. I don't think this would simplify any further. I think that's as simplified as it goes. The other one, that'd be good, right? There's gonna be Boolean algebra on it. There's gonna be a question and it's gonna say like, show your work, show each step. I probably won't call out, make you write every single identity like I have you do in the beginning, right? The first couple of exercises that have you call out all the identities are just to help you remember what they are and what they do and help reinforce that association between Boolean algebra and regular algebra. But this would be a good one. This is F on homework 3. So there's a couple ways we can do this one. We could start with De Morgan's, or we could multiply the A through first. Either option is fine. You'll get the same answer as long as you're careful. The multiplying through is a little bit more risky because you just have to make sure that you don't mistake that bar and like overextend it. But regardless, we're not going to get away from doing De Morgan's, right? You can safely assume that there will be a De Morgan's operation somewhere on the exam. And so here we would do De Morgan's, and we won't mess it up like I did before. Flip the gate, invert the variables. This is technically as simple as I would expect you to. If you were building this on a bench and you had access to all of the gates, there is one more operation that I could do. Does anyone see it? This is not one. One would be right. By splitting those, I get something entirely different. X NOR, because it is true when they match. If B and C or not B and C. So 0, 0 or 1, 1, which is the opposite of XOR. This is an XNOR. So this is equal to A and B XOR C R. Because B XOR C, and then I have to invert it because it's XNOR.
The third line down is pretty much what you'd expect.
Yes, this is all I would expect is this first one. Unless I say something like your final expression should contain an XOR or XNOR gate. I will give you a hint that you would need to kind of identify that kind of thing. That is actually, I saw some worried looks. Don't worry, it actually makes more sense because it means when you get down to the final expression, if there's not an XNOR gate or XOR gate available, it means you did something wrong and it's just another check. So. Okay, so I did timing. I did a couple of Boolean algebras. I think that covers the ones that I can universally say people worry about. Does anyone have other topics for concern or other examples they would like me to do, homework problems they'd like me to solve? Give you a moment to think. Yeah. The 3 input gates with the MOSFETs. That's a good question. So we kind of went over the X4 gate, right? In every case that you guys are going to need to be worried about for this class, if you have to draw it, you will be able to do so through a pull-up network and a pull-down network. One of them will be in series, one of them will be in parallel. That's all that will happen. I may ask a question where I draw one and I'll have to ask you, like, is there a condition in which this would light on fire, basically, right? Is there a bad situation? So this was our X4 essentially, right? Let's double check that. So if A is 0 and B is 0, then we're going to get 0, 0 makes a 1, and any other combination makes a 0, XOR. So if I want 3 input,
That'd be a door. That's excellent.
X, sorry, why don't I got stuck on that? It would be a NOR gate. Thank you. Yeah, I'm gonna stuck on the XORs. So because you guys can analyze your own, since you're going to be designing this kind of pull up, pull down relationship, the CMOS, right? The complementary MOS, which has the relationship between the NMOS and the PMOS devices. PMOS have the little bubbles, they go on top. The only thing that I have to change to go from NOR to NAND is the bottom becomes 0 and the top becomes parallel, but I keep the PMOS on top. But if I want to make it a 3 input gate, what do? I need a C in here somewhere.
Another PMOS and NMOS.
Yeah, I just add another of each gate type. I just add another input. Right now, this will be, now I need A, B, and C all to be on. I need all zeros in order to get a 1. Otherwise, I'm going to get a 0. And in order to drive the 0 over here, I just need another one in parallel. So just straightforward, we add another one to each side of the pull up or pull down network. If I wanted to do that for 4 inputs, I would add another one in series and another one in parallel. Yes.
No matter what signal connects to your PMOS and your NMOS, like doesn't matter when you have A at the.
Yeah, so if you're wondering this.
Well, like more or less like which one it splits off to, like.
Oh, so you're wondering more like.
Yeah.
Yeah, no, that doesn't matter. Again, it just has everything to do with the fact that circuits are linear and kind of the organization of things. So the serial organization doesn't matter and the parallel ordering doesn't matter. So they're pretty flexible. You don't have to stress too much about that. It is more likely, I mean, the 2 things I'm likely to ask around this topic, right, would be to evaluate a gate. If I put something up with transistors, CMOS devices, and ask you to draw a truth table for what happens, right? If there's a situation where it doesn't make the output 1 or 0, then you would put Z. Okay. And this is kind of a weird way to do it. If it ends up being dual driven, which is to say it's trying to make it 1 and 0, if the pull up is connected and the pull down is connected at the same time, you're going to hate this, but when you go into VHDL and you start simulating it, the variable it ends up putting is an X, which to us looks like a don't care. It's okay if you don't know that, because basically what you're going to do, what I would recommend doing is what I did last time, where you're going to basically say there's a pull up network, there's a pull down network. And so in the case of the pull up, it's either 1 or not connected. And in the case of the pull down network, it's 0 or not connected. But if I built a bad one, if I give you like a bad gate and you do this pull up, pull down, and say you end up with something like this. Now I see the pull up is trying to make it 1 at the same time the pull down is trying to make it 0. Then you could just, and the question there would be like, is there a flaw in this design? Then you would just go like, there's my issue. Right. And I could ask it in terms of Ohm's law, like, according to Ohm's law, why is this a problem? And then you would just draw the circuit that would say something like, well, I have this and I have this, so I have it. And even though there's an open switch over here, I still have a path to ground. Ohm's law says V is equal to IR. Current is our issue, so I is equal to V by R. But there is no resistor here. So our current is what? Infinite, so it breaks. That's the kind of thing that you should be aware of when you start evaluating if I give you a CMOS device. Other questions that you guys are worried about? If not, I will just go find something inside of our homeworks. I feel like you guys are doing good in, oh, actually, there's a good one to do. Where is it? It's okay, we can just make it up. I've done this example a bunch of times with people, various others, but I think it helps to come back anyways because it is so close to important design, which was the dice question, right? Where you have a table that shows you that we have an arcade game and you want to push a button and it's going to roll a dice and it's going to show you the results of that dice. The die has results between 1 and 6, right? That's what a dice can roll. Can't roll a 0, can't roll a 7. And our truth table says that I need to figure out, I mean, you're provided for it, but if I were just to ask you this, I says, go ahead and design this for each of the lights, right? You've been given a couple of simplifications already, which is it said that certain lights, I think A and A are always on together, so they're the same light. This light, I think, stands on its own, so it needs its own signal, for example, so that's A, that's D. And then when you're asked to design the circuit, the first thing you go is, well, in order to represent the numbers 1, 2, 3, 4, 5, and 6, how many bits do I need?
Three bits.
I think the homework showed that was
3 bits.
3 bits.
Because 2 to the 2 is 4, which does not have enough spots to contain 1 to 6. Whereas 2 to the 3, this is the number of bits, is 8, which does have enough room to contain the numbers 1 to 6, right? That's what this is saying, is I need to be able to represent B0, B1, B2, all numbers 0, 1, 2, 3, 4, 5, 6, 7. I really only care about a subset of those. Sorry, I don't know why I did that way. Right, 1 to 6, those are my possible results. There's a couple of extra. This is a normal situation that we're going to run it all the time, where we don't use every single possible combination, which is to say, we don't have 0, 0, 0 or 1, 1. I'm way off on that. 1, 1, 1. Right? I don't have either one of those. So what does that mean for my output A? Well, because my roller, whatever is generating this number, will never put me a 0 or 1, I just don't care, right? And don't cares arise when there are situations that can't happen or shouldn't happen. We don't really care what the result is, right? And it just allows us to simplify the K-map, right? That's what the don't cares are useful, is because we got to pretend like it is a 0 or a 1, whichever is most convenient. Can't roll a 7 either. On a 6-sided dice, there's just not 7 sides. So now I say, well, in the case of 1, if I roll a 1, well, we have a little diagram and it says this is what a 1 looks like. So is A on when it's a 1? No, right? A is off. D, however, also has that don't care, but is a 1 if I roll a 1. Because 1 means on, it's turned on that light. Well, if I roll a 2, then I have an A, but I don't have D. If I roll a 3, well, threes look like this. So I have A and D. Four. I have D, or rather A, but not D. Five. I keep D or A and add in D. And 6. Still got A. Don't have D. And I can do that for every other light. Right? This is your kind of design thought. The most important one is assigning the correct number of bits. And as you've just witnessed, it's hard, right? It's hard to think like this, but it all comes down to, if I have 3 bits, how many options do I have? So if I give you a story problem that requires a certain number of choices, and I ask how many bits should be assigned for this, that's how you do it. Make sense? And now it's just a K-map. And I think most of you understand K-maps. I'm going to try and at least, there's a couple problems that I'm going to try and get graded before your exam to make sure, because until I have like looked at your guys' exams, I can't know. I just talk to you guys in labs. You guys sound smart in lab, but I can't tell if you're just good at faking yet or not. So I will try and check some of your K-maps. I will try some check these. But I will post the answers. So use them, compare them to yours, make sure that you understood them. If you don't, talk with your fellow classmates or email me or look up the internet, try again, right? It's very important that you understand how to do it right, because right now, unfortunately, I've been behind on it and I haven't given you the feedback. So you've submitted the homework and you don't know if you know it yet or not. So once I get the homeworks rolling out on Friday is when I plan on doing all of them. Make sure you use them to check, because otherwise we don't know if you know yet, okay? And all that is to say, I think based on talking to you all, that you would understand how to turn this into a K-map. And I have 5 minutes, so do A, right? I need a K-map for every output. I cannot build a K-map that uses more than one output. So this is my K-map for A. Let's put this slowest changing one, which is to say B2 over here. So we're all on the same page when I go through the answer. And then I think that will make this B1 and this B0, because then when I have 0, 0, 0, 1, 1, 1, 1, 0, I go from B1 changing, nope, I'm gonna flip those. There we go. Let's do that mapping.
since K-maps don't care about it, don't cares, could we put a 0 in the first X and then a 1 in the other one to simplify it?
Yes, basically. So I don't ever rewrite them. I just remember that. So did everyone get this? At least this far, right? This is a big chunk of the points. Be very aware that when I grade these, if I ask for sum of product versus product of sums, that's a significant portion of the points. When I grade that is reading the instructions. Reading the instructions on these problems clearly and making sure you understand them is very important. Because if you circle the wrong ones, then there's a problem. Because this one's kind of interesting, because if I do product of sums here, it's just one implicant. Whereas if I do sum of products, well, it's not really much more difficult. It is a little bit more. But what we were talking about up here, if you couldn't hear in the back, is pointing out that can we pretend this is a 0 or write a 0 and write a 1? And the answer is yes, right? Because that's the whole point of don't cares, is whichever is more convenient. So if you'd like to go in and after you've done it, rewrite them as the 0s and 1s, you could. I would worry about that if you're not careful, right? Because you could lose track. So what I do is I just remember that I don't need to include the X's, the don't cares, in coverage. If it's not covered, that's okay if it's an X. So when I do the sum of products, I've got 4 there. I got 4 there. Done. Yeah. Because along here, B2 doesn't change, right? Because that's, we love rows and columns because it's really easy to see. So B2 doesn't change. Or the other implicant. And now this one, B2 obviously changes. B1 doesn't. B0 does. So we have B2 or B1. There, we did it. We would rinse and repeat the same K-map for the lights, right? Well, I shouldn't say the same K-map. It's best to do the same mapping just to keep your mind straight because it speeds things up. So if I do B2, B0, B1, when it's time to go and fill in D now, I already know the order of these, so it doesn't take me any time to evaluate because I've already gone, well, I went X0, 1, 1. So now it's X1, 0, 1, remembering to flip those two columns. And then that's X1, 0, 1, 0, 1, 0, X, 0, 1, 0, don't care, right? Flipping those columns is super important. Or take whatever notes you need to put in your little summary to make sure you don't mess those up because that too is a lot of points to miss.
That's just B0.
Yeah, we circle that. B2 changes, B0 doesn't. Therefore, D is equal to B0. Ta-da. Right, we built an arcade game. Well, part of it, anyways.
Just rolling dice. It's fun, right?
It's not impossible by the end of this class. We have to end up here. You guys can go ahead and start cleaning up because I'm out of time. By the time you get to the end of the class, you could actually really start building like old school arcade games and digital logic fairly easily.
So were a lot of the classic arcade games just made in circuitry rather than?
I mean, that's kind of how you started because it was difficult. They didn't really have any of the automation tools that we have now. So they were kind of custom building these chips to take care of all of that.
Machine for assembly, basically.
Yeah. Well, there were two ways to do it.